Okay, so this one is just an extension of yesterday's, which hopefully you guys didn't check for that one at like 3:30 and then give up, because I posted it at 4. But yeah, it's this is basically just taking that concept of solubility a little bit further. And if you understand equilibrium, I don't think the solubility stuff is too bad. It's just kind of now we're talking about solid and liquid equilibrium instead of the acid-base equilibrium that we've been talking about. So again, just kind of as a reminder here, the typical sort of equilibrium we have, I don't know, I think one of the examples yesterday was Ag2CrO7. Not that soluble in water, but there will be a little bit of equilibrium going on there where you'll have some of the Ag plus ions and then some of the CrO7 2 minus ions. Okay, and so that you can think of that as being an equilibrium, and there's the K for these kinds of reactions. These kinds of reactions where you put a solid into a liquid and it's it's doing equilibrium. They're common enough that we give it a name, KSP. And so now we're going to talk about some of the things you can do to affect the solubility. Now you have to be careful here because these things are not going to change the KSP. Okay? What's the only thing that can change an equilibrium constant? Temperature. Okay? So when we talk about all these other things here, the presence of common ions, pH of the solution, formation of complex ions, those are not going to change the KSP, but they are going to change the solubility. Okay? In other words, they're going to change how much of this solid will dissolve in the solution. Okay? But you'll see how that works. I mean, we just have to remember the KSP is not going to change unless we change the temperature. Okay? So presence of common ions can do something to the equilibrium. If we change the pH of the solution, that can actually change the solubility. Some things dissolve a lot better in a lower pH. Some things dissolve better in a higher pH. Okay? And then a formation of complex ions, we're going to talk about that a little bit. I don't know how we did this last year. I did all of this stuff before we'd even talked about complex ions, which doesn't make a lot of sense. So I think this is number 3 here is going to make more sense to you guys because we've already talked about complex ions this year. Okay, so presence of a common ion in a solution will usually decrease the solubility. Again, not the KSP, but the solubility of the substance being dissolved. Okay, and we can conceptually we can think about this in terms of Le Chatelier. I'm going to talk about Le Chatelier quite a bit today. Now, calculation-wise, we're probably going to have to use an ice table for this, but if they ask you a conceptual question, you could just think Le Chatelier on these. Okay, so an example here: if we add sodium fluoride into a solution that already has calcium fluoride, that's going to cause the solubility of the calcium fluoride to decrease a little bit. Okay. So let's think about this for a second. Actually, do I have a... Nope. Okay. So let's just think in terms of Le Chatelier here. So I've got CaF2 in equilibrium with the calcium 2 plus and the 2 F minuses, right? So that's my equilibrium. Now remember, Le Chatelier, we mess with the equilibrium a little bit, and we figure out how it's going to, which way it's going to shift the equilibrium. Okay? This is a solid, by the way. I guess I should label that. So if I put NaF into the solution, well, the Na doesn't really matter, right? Because that's not, we don't have any sodium in this reaction at all. But I'm adding more F minus into the solution. I'm adding more of this. What does that do to the equilibrium? Pushes it back towards the reactants, right? Okay. In other words, it decreases the solubility. And what that means is, when I say solubility, I want you to be thinking about how much of this is dissolved, how much of the CaF2 is dissolved in the solution. Okay. So in other words, I put the F minus in here. That extra F minus starts to react with some of this Ca2 plus to go back to CaF2 solid. So I increase the amount of solid that's in my solution at that point, and I decrease the amount of calcium ions that are in that solution. Does that make sense? Okay. So if you think about your KSP, again, because we're adding F minus, the concentration of F minus is going to increase, but the concentration of the Ca2 plus is going to decrease. Okay, so again, that's going to balance out so that you have the same KSP at the end of this thing. By the way, just to review in case you did not get to watch the video last night, if I write the equilibrium expression for this reaction, what's it going to be? It's just going to be the product of the products, right? Because products over reactants is our typical equilibrium expression, but we don't put solids in our equilibrium expression, right? So this is just going to be Ca2 plus times. Now here's where you have to start thinking about coefficients again. It's been nice with acid and base stuff. We didn't have to worry about coefficients, but there's a 2 in front of that F minus, so now this has to be F minus squared. Okay. So there's your equilibrium expression for that one. And like I said, when we add F minus here, the concentration of the F is going to go up. But ultimately, because the equilibrium shifts to the left, the concentration of the Ca2 plus is going to go down, and so our KSP is going to stay the same. Solubility product constant. And I guess constant spelled with a K. Solubility product constant. I don't know. It's the equilibrium constant. I don't know who decided that was going to be K in the first place. Alright, so here's a problem. Now, here we have to think mathematically instead of just conceptually. So Le Chatelier will help us to check our answer maybe, but it's not going to help us to get a number. So here we probably have to use an ice table. Calculate the molar solubility of CaF2 at 25 degrees Celsius in a solution that is 0.010 molar in CaNO32 and 0.010 molar in NaF. Okay. And then it's giving you the KSP here. Fairly small, right? What does that tell you about CaF2, by the way? If the KSP is small, what does that tell you about its typical solubility? Not very soluble, right? Okay, it's not going to dissolve very well in water to begin with, okay? So probably the best thing to do here to start with is to actually write the reaction. CaF2 solid, and we did this on the last screen, but I'll rewrite it again. Okay, so let's go ahead and make ourselves an ice table here, and I'm going to have to make 2 ice tables on this one because we've got an A and a B here. But for the first one, again, we don't care about this portion of the ice table because it's not going into our equilibrium expression, right? So it doesn't really matter how much of that we have to begin with. Let's see. The concentration of the Ca2 plus to begin with on this first one. Okay, let me back up a little bit. So yesterday, again, in case you didn't see the video yesterday, what we were typically doing on these is we were saying we assume that we have all CaF2 solid to begin with. So none of these at the beginning, and then as this starts to dissociate, then we end up with some of these. Okay, and we would call this X and 2X. The difference here is we can assume that we have none of the F minus to start with, but this is a solution that also contains CaNO32, right? So initially we're going to have some calcium, some Ca2 plus in that solution, and we're going to have 0.010 molar of it. Does that make sense? Because we already have some of this, so this is going to be, it just changes our initial concentration here in our ice table instead of being 0. Okay? So then we still have, because there's none of the F minus, the equilibrium has to go this way, right? So this is going to be plus X. Here's where you have to be careful again. We haven't had to worry about this for a while. This is plus 2X, okay? Because remember, in the change row here, you have to pay attention to the stoichiometry. All right? So this is going to be 0.010 plus X, and this is going to be 2X. So, and now our KSP is 3.9 times 10 to the negative 11th, so we just plug this into our equilibrium expression here. 3.9 times 10 to the negative 11th is equal to, and here's, again, you have to be especially careful here, because here's our equilibrium expression for this one. The F minus has to be squared, right? So you really have to watch that. So the Ca2 plus here is, I'm going to run out of room. I should start this lower. 3.9 times 10 to the negative 11th equals 0.010 plus x times 2x squared. Well, this is just kind of a mess, isn't it? We're going to end up with a quadratic here, and I would prefer not to. Actually, this isn't even a quadratic because this is squared, so then when we multiply that by the x, we're going to have an x cubed term, and then some other terms as well. And I'd prefer not to have to mess with that. So our simplifying assumption comes to the rescue again here. All right, this is a small KSP, right? Small k, so we can assume that the amount of calcium 2 plus that comes from the dissociation of the CaF2 is not that much compared with the amount that we already have in the solution. All right, so 0.010 plus x, we'll just call that 0.010. Okay, and that's going to make this a lot easier. All right, so then once we calculate all of that, we end up with 3.9 times 10 to the negative 11th is equal to 0.04 x squared. Okay, and then when we solve for x here, we're getting 3.1 times 2 sig figs, yeah, 3.1 times 10 to the negative 5th for my x. Okay, and what are they asking for here? They're asking for the solubility of the CaF2, okay? Here's kind of the nice thing about these problems. Usually once you solve for x, that is your molar solubility, okay? In other words, that's how much of the CaF2 is going to dissociate. Does that make sense? Okay, so the molar solubility here is going to be 3.1 times 10 to the negative 5th molar. Okay? Now, how does that compare with the molar solubility we would have if we didn't have any of the CaNO32 in the solution? Is this lower or higher, do you think? Remember Le Chatelier, right? We put some extra Ca2 plus in the solution. That's going to push the equilibrium towards the CaF2, right? Okay, so that means that less of the CaF2 will actually dissolve than it would have if we hadn't had any other ions in that solution. Okay, so we would expect the solubility to be a little bit higher if there was nothing else in the solution. And actually, you can check that fairly easily because your KSP expression there would be 3.9 times 10 to the negative 11th is equal to, what would it be? This would have been x, and that would have been 2x, so then that would be x times 2x squared. So then you'd end up with 4x to the third. If you figure that out, take the... You guys know how to punch that in your calculator, by the way, the cube root thing? Okay, just wanted to make sure, because you might have to do that every once in a while on these. So your x ends up being 2.2 times 10 to the, or 2.1, I guess, times 10 to the negative 4th. Okay, so notice that's a little bit bigger number than this. Okay, so our solubility actually is a little bit higher if there are no other ions in that solution whatsoever. Okay, but since we have ions in the solution, it's going to be lower. Since we have common ions in the solution, I should say. It doesn't matter if you have ions in the solution, but since we have Ca2 plus ions in there. Okay, and then letter B here is asking, what if we have 0.010 molar in NaF? Well, wait a second. Is this going to be exactly the same? Because we have the same concentrations, right? The problem is the stoichiometry here, so we actually do have to recalculate this, right? Unfortunately. So let me clear out my ice table here. I know you guys can't do this, but I can. Let's see, I'll even keep this. All right, so now we're starting with, again, don't really care about this. We're starting with 0 of the Ca2 plus, okay? But we have 0.010 molar in the F minus, okay? And so again, this is going to be plus x and plus 2x, right? So then we end up with x and 2x plus 0.010. Well, we're pushing it a little bit here. But do you think we can still make our simplifying assumption on this one? Can we assume even if we multiply the solubility by 2 that it's still not going to be as significant as 0.010? Okay, I'm okay with that. So, and the main reason I'm okay with that is because I don't want to have to solve this thing otherwise. And they're not going to make you solve this thing otherwise on the AP exam because you just don't have time for that. So, yeah. Yes, you can make that assumption on my test and on the AP exam. Alright, so what we end up with here when we plug this in, we're going to have, this actually ends up being a little bit easier, because we're going to have x, and then instead of 2x plus 0.010, we're just going to put 0.010, right? We can drop the 2x part of that expression. So then all you have to do is, what's that? Oh, I'm sorry, yes, thank you. 0.010 squared. So 3.9 times 10 to the negative 11th. Divided by 0.010 squared. So we end up with the solubility of 3.9 times 10 to the negative 7th on this one. Does it make sense that the solubility is lower if we put fluoride in that solution as opposed to if we put calcium in that solution? I'm seeing some yeses and some nos. Why would it make sense? Okay, so there's more of the fluoride that dissociates there, okay? So because of that, it's going to have a greater effect on the solubility. Okay? Alright, so that's that. Now, we got to talk about pH. Yeah, pH and solubility. This one's moving kind of slow. Hopefully it'll start moving a little faster here. So when we talk about pH and solubility, that comes into play on a couple of different occasions. Usually it comes into play, you guys can shut that window if you want. Yeah, go ahead. It comes into play when you have a base that's dissolving, okay? And that's when the pH will really have an effect on how well it dissolves. So let's say that we've got MgOH2, right? It's got a KSP of 1.8 times 10 to the negative 11th, and we want to figure out what is the Mg2 plus concentration, what's the OH minus concentration in this solution. So again, you got to kind of think in terms of an ice table here. We've got our magnesium MgOH. Sorry if I didn't give you enough room for this. I didn't give myself enough room for this for sure. Mg2 plus 2OH minus, right? And again, you have to be careful and make sure when you write these equations that they're balanced. Okay? Since we have 2 OHs on this side, we have to have 2 on the other side. And then, so then if you make an ice table for this, you're going to end up with, we're going to start with 0 and 0. We're going to end up with x, and we're going to end up with 2x here. Right? Everybody following so far? So then if you plug that into your KSP expression, you've got, let's see, 1.8 times 10 to the negative 11th is equal to x times 2x squared. And again, we just talked about this. Does everyone understand where the squared part comes from? Okay. So then we end up, and you know, you're going to get to a point maybe on these where you see the solubility like this with a 1 to 2 stoichiometry, and you're just going to remember, oh yeah, that's 4x cubed, right, without even doing an ice table. If you get to that point, that's good. Just be careful, because, I mean, if it's a 1 to 1 stoichiometry, it's just x squared, right? But if it's a 1 to 2, then it's going to be 4x cubed. So then when you solve for that, your Mg2 plus concentration is going to be your x. So we've got 1.8 times 10 to the negative 11th divided by 4. and then, whoops, take the cube root of that. I'm getting how many sig figs? 1.7 times 10 to the negative fourth. Okay? So that is your concentration of the Mg2 plus, right? Does that make sense? Let me erase this so that I can write that clearly. I'll keep my x. So this is 1.7 times 10 to the negative fourth molar. What's the concentration of our OH minus going to be? It's going to be twice that, right? Because it's going to be 2x, since there's 2 OH minuses for every 1 Mg2 plus. Does that make sense to everybody? Okay. So, double that number, 3.3 times 10 to the negative fourth. Okay, so then how do we figure out our pH? If we want to know the pH of our solution. We have the OH minus concentration. Okay, so take the negative log of that. That gives me the POH, right? And then I subtract that from 14. So the negative log of this number gives me 3.48 or something like that. If I take 14 minus that number, it gives me a pH of 10. We need 2 sig figs here, so 10.52. Okay, so that's my pH. 10.52. Hang on just one second. Okay, sorry about that, here we go. So, let me rewrite this. We decided our pH here was 10.52, right? Okay, and that's just determining the OH minus concentration, take the negative log of that, and then subtracting it from 14. So the question is, what if we put this into a more acidic solution that when it reaches equilibrium it has a pH of 9? Okay, so let's kind of think about this for a second, because again, and I'll rewrite my solubility equation. Huh? On this? It's just asking what's going to happen. Yeah, we're thinking conceptually here. There's no real math on this one. Okay, so let's just think about this for a second. If we put this into a more acidic solution, then what is there going to be extra of in that solution if it's acidic? It can be H+, right? What is that H+ going to do? It's going to react with the OH minus. So in other words, we are, in effect, we are taking some of that OH minus out of the solution, because the OH minus is going to react with the H+, right? So let's think Le Chatelier. We're taking a product out of the equilibrium. What's that going to do? Okay, it's going to shift it this way. So what that means is more of the MgOH2 will then dissolve. Does that make sense? We're going to have more of the Mg2 plus in there. Now, we're not going to have more of the OH minus because the OH minus is reacting with the H plus, right? But we're going to have more of the Mg2 plus at that point. So that's the effect that this is going to have. Now that's conceptual, okay? We can actually figure this out. Let me see if I gave us a space for that. Whoops, this was your space for that. Sorry. Yeah, the next little part was the part where we were supposed to talk about Le Chatelier. I apologize for that. I actually like it better this way though, because I think it makes more sense to talk about it in terms of Le Chatelier before we figure it out, just to think conceptually. So, okay, so here's how we would actually figure this out. What we have to do is figure out how much OH minus we actually have in the solution if we have a pH of 9, right? So let's think about our equilibrium here, and for this one it's probably useful to make an ice table, and I'm sorry, I know you guys probably don't have room for all this. I'm going to make an ice table over some of this writing. Let's assume that we have none of either of these to start with, okay? But we put this into a more acidic solution, and it's going to have a pH of 9. What is that telling me about my OH minus concentration? It's going to be lower, right? So let's figure out exactly what it is. If I have a pH of 9, if I 10 that, right, then I get 1 times 10 to the negative 9th. We can actually do this one in our head. Or, you know what, let's do it the other way. I think it's easier. What's the pOH of this solution? 5, right? So the OH minus concentration would be 1 times 10 to the negative fifth, okay? Okay, does that make sense? Because our pH is 9, our pOH is 5, so our OH minus concentration at the end is 1 times 10 to the negative fifth, okay? That means now we don't have to work with X's and stuff like that. We've actually got, we can figure out our Mg2 plus concentration based on this, right? So that means this increases by 1 times 10 to the negative fifth. If this increases by 1 times 10 to the negative fifth, then how much does the Mg2 plus increase by? Half of that, right? Okay, which is 0.5 times 10 to the negative fifth, which is 5 times 10 to the negative fourth, right? It's a good opportunity for mental math right here. Okay, so what that's telling us here, if we want to actually know numbers on this, now our solubility is going to be equal to the Mg2 plus, right? Because this is a 1-to-1 stoichiometry here. So as much Mg2 plus as we are forming, that's how much the MgOH2 is dissociating. So our new solubility is now 5 times 10 to the negative fourth. And let's see, what was it before? I can't remember. What was our Mg2 plus concentration before? 1.7 times 10 to the negative fourth, okay? So you see how the Mg2 plus concentration has now increased a little bit. Okay, we didn't change the pH that much, so it's not going to change a ton, but it did increase. Okay? So that's kind of how that works. So the basic thing that you have to understand here, okay, this is what I would remember, is that if we decrease the OH minus concentration by putting it in an acidic solution, that's going to shift the equilibrium towards the products, because we're taking out, you can think of that as taking out one of the products. When we do that, it pushes the equilibrium towards the products. Okay? Alright, so putting the MgOH2 into a more acidic solution greatly increases its solubility. Now, if we put it into an actual acidic solution, that was just a pH of 9, right? So that's still a basic solution, but it's a little bit less basic than the one we started out with. So if we put this into a much more acidic solution, you can imagine the solubility would greatly increase. Okay? Alright, will this also work with a compound that doesn't contain OH minus? What do you think? Okay, let's think about it conceptually. So the equation for a solubility equilibrium here, CaF2, solid, okay, now again, when we put that into an acidic solution, the acidic solution has H plus ions, right? What might the H plus ions do? React with the F minus, right? This is a weak base. Okay, so we still are taking the F minus out of the solution, which pushes the equilibrium to the right, towards the products. So the exact same thing happens if we have a weak base as if we have OH minus. Does that make sense? Because the H plus is still going to react with it. Now, what if I had something like, do I have an example of this? No, I don't. Okay, so let's talk about this. What if I had calcium chloride? Would putting that in acidic solution increase the solubility? Why not? Okay, because this H, the H plus ions here, are never going to combine with the Cl minus ions and take it out of solution, because that would form a strong acid, and that doesn't happen, right? Okay, so it has to be either a weak base or OH minus for this to work. Okay. So, oops, here's a graph. So, I mean, you can see this has a huge effect on the solubility of CaF2. If you look at this graph, now this graph is kind of backwards, okay? Notice the 7 pH is over here, the 1 pH is over here, but all they're showing is as the solution gets more acidic, the solubility increases, you know, exponentially. Okay, so that's a huge, dramatic rise in solubility. Okay, so the general rule here, the solubility of slightly soluble salts, if they have basic anions, then the solubility is going to increase as we put more H plus into that solution. Okay? Now, if the anion is not basic, in other words, like chloride, nitrate, any of the ones that would form strong acids if you put a hydrogen on them, then it doesn't affect the solubility if you put H plus in there. Okay? Alright, which of the following substances will be more soluble in acidic solutions than in basic ones? But this is not asking you to put anything in order. It's just asking, look at each of these individually and tell me if we put this in an acidic solution, would it increase the solubility of that particular substance? Okay, what about the first one? Okay, I'm going to say yes for this one because that's got OH minus in it, right? So that's definitely going to react with the H plus, and that's pushed our equilibrium to the right. What about the CaCO3? So CO3 2 minus, would that react with H plus? Yeah, I mean, H2CO3 is not a strong acid, right? HCO3 1 minus is, that can definitely form. Okay, so I'm going to say yes to this one as well. You got to remember your list of strong acids here in order to be able to answer this question really well. What about BAF2? I would say yes on that one too. I mean, we already looked at one that had a fluoride ion in it. What about AgCl? There we go. That's the no. Yeah. Okay. So that's fairly simple, right? I mean, I think the kind of question they would ask you about that would probably tend to be conceptual rather than calculation-based. And then the last one we need to talk about is the formation of complex ions. Okay, so this can also, it sort of has the same effect as pH in that it's going to pull one of your ions out of solution. Okay, and so you got to remember, just based on Le Chatelier, when an ion gets pulled out of solution, that's going to shift the equilibrium to the right. Okay, so again, we talked about metal ions can cause a water solution to become more acidic because they're going to form complex ions, coordination complexes. You guys remember talking about that? Okay. So that's what I just said. So the metal ions can also interact with bases other than water. That could affect the solubility as well. So let's take a look at that. That's the same thing again. So the example here is AgCl that's added into a solution which also contains the weak base ammonia. Now, this is going to have to be fairly concentrated, the ammonia is, in order for a lot of this to occur. But we still could have a little bit of an effect here, even if there's just a little bit of ammonia. So the equilibrium we need to think about here is the AgCl solid in equilibrium with Ag plus and Cl minus. Now, if there's some ammonia in that solution as well, what might the ammonia react with? Okay, remember, ammonia is actually a good ligand. You guys remember talking about that? Okay, and it's been a while, okay? But a good ligand has a lone pair of electrons on it. Remember, this is the Lewis acid, Lewis base stuff that we talked about, okay? I wasn't telling you to change your answer, I was just explaining it, okay? So, the NH3 here, that's a good electron pair donor, okay? And the silver right here with a 1 plus charge, that's actually a good electron pair acceptor, okay? So Ag plus, that's going to be your Lewis acid here. NH3 is going to be your Lewis base. This, every once in a while, might react with this to form a coordination complex, okay? Which is probably going to be AgNH3 2, right? Because twice the charge. Okay, so we don't really have to even think too much about that other reaction, other than what's it going to do to the amount of silver ions that we have in the solution. It's going to decrease them, right? We're pulling some of this out so that it can react with the NH3. And what net effect is that going to have on the solubility? It's going to push it to the right. In other words, it's going to increase the amount of AgCl that dissolves. Does that make sense? I'm getting a yes and a no at the same time. Yes? Okay, so again, because we're just taking some of this out, the Ag+, then more of the AgCl has to dissolve to sort of maintain equilibrium here. Okay. Okay, good. So for a base like NH3 to increase the solubility, it's got to interact more strongly with the metal ion than water does. Okay. In other words, there are water molecules surrounding this Ag+, right? And we haven't talked about that in a while, but I know I showed you at the beginning of the year how when something dissociates, when something dissolves, the water molecules surround it because they're attracted to it, right? You remember talking about that? The NH3 kind of has to fight its way through those water molecules in order to bond with the Ag+, okay? So the attraction of the Ag+ to the NH3 has to be stronger than the attraction of the Ag+ to the water molecules in order for this to actually occur. So there's something called the Kf, and I don't think this is going to come up on the AP exam, but there's a letter for, you know, there's almost every letter in the alphabet for K, because there are so many different kinds of equilibrium constants. But basically, if we can look at that formation constant, okay, if it's a large formation constant, that means that this complex ion is likely to form in water. Okay, so it gives you sort of an idea of, if it's big, this probably will happen. If it's small, it probably won't. Okay, but again, I've never seen a question like that on the AP exam, so I'm not too worried about that, other than maybe you just know it. But here's the general rule that might be helpful to remember. If you put a metal salt into NH3, Cn-, OH-, one of those, then it's likely that that metal will form a complex ion, okay, which is going to take some of that cation out of the solution, okay? So ultimately what you need to remember is just this, okay, that if you have it in a solution where it could form a complex ion, you're probably going to lose some of the cation, some of the Ag+, and that's going to increase your solubility, okay? Here's an example of some formation constants, and you know, you can see most of those are fairly large. So these are the kinds of ligands like NH3, Cn-, maybe S2O3. Those are the kinds of things that might pull a cation out of water and form a complex ion with it. Okay. But the ones, like I said on the last slide, the ones you really probably should remember, ammonia is a big one. Cyanide, I don't know about that one. OH- you would probably see a lot. So definitely ammonia and OH- are ones that are really good to remember. Okay? Alright, calculate the concentration of Ag+ present in a solution at equilibrium when concentrated ammonia is added to 0.010 molar solution of AgNO3 to give an equilibrium concentration of NH3 equals 0.2. Okay, neglect the small volume change that occurs when NH3 is added. Alright, so here's the basic idea of this. So we've got AgNO3 in solution, right? So the first thing we've got to think about is our equilibrium here. Now this should be fairly soluble to begin with because this is a nitrate, right? And what do we remember about nitrates? They typically dissolve, right? Okay, you remember that from your solubility rules? Okay, so, but I didn't give you enough information here. Oh wait, maybe I did, because you have the equilibrium concentration, because they're just asking for the concentration of the Ag+. Okay, so what we've got here, if we're thinking about our ice table, we've got none of this, and we're gonna, or not none of this, we've got a lot of this, but we're gonna ignore it because it's not in our equilibrium expression. We can assume we have none of the Ag+ and the NO3- to begin with, okay? So we've got a 0.010 molar solution of AgNO3, and that's giving an equilibrium concentration of 0.2. Oh, sorry, hang on just a second. Okay, So I paused it so that I could come back and tell you we're going to call it quits on this one. We can... That would have been an awkward stop, though. All right, so we're gonna cover this last sample problem in class. If we cover it at all, this honestly is not going to be on the AP exam, but I like the question, so we'll probably end up covering it anyway. All right, we'll see you in class.